At noon today, light slowed by 1%. The immediate takeaway is simple, and it is unsettling. Clocks, forces, and GPS would start drifting within minutes. Traffic lights would still change, but timing would feel off. Radio links would lag, while lasers would arrive a hair late. Your eyes would not notice right away, yet instruments would. This tiny change touches everything that uses time. It also gently nudges how atoms hold together. Here is how that shock ripples through reality. You send a photo across town and the fiber hums. That hum is light, slowed inside glass by its rules. The speed of light in vacuum is a constant. It equals 299 million meters each second. It is not just a speed limit for signals. It also sets the scale for electricity and magnetism. That is why a small change ripples into every wire. Electromagnetic waves exist because changing fields chase each other. Electric fields spawn magnetic fields, while magnetic fields return the favor. Their dance has one built-in tempo, called c in equations. C equals 1 over square root. That root is epsilon naught times mu naught. Those constants describe how space permits fields to form. If c shifts, those permissions change together, or something else must give. Example in real terms. A 1,000-kilometer fiber adds 5 milliseconds of delay. Knock c down by 1% and you add 50 microseconds. That sounds tiny, yet traders pay millions to shave less. A continent-wide exchange would feel that nudge immediately. Deep space links would stack the delay over hours. Rule of thumb, timing errors scale with distance. They scale linearly with whatever new c you get. If c sinks, every journey takes longer by that fraction. Bottom line, c is not just a number on paper. It is the metronome behind electricity, timing, and every data hop. Strike a match in a dark room and watch the glow. That color comes from electrons stepping between energy levels. There is a small number that sets those steps. Physicists call it alpha, the fine structure constant. It is about 1 over 137. It controls how strongly light couples to charged particles. If c changes, alpha changes as well in most frames. Bigger alpha means stronger pull on electrons around nuclei. Why care about that shift when fire still burns? Because chemistry is a balance between attraction and motion. Electrons are tethered by the electromagnetic force, and they orbit by motion. Stronger pull tightens orbits, while weaker pull loosens them. Those shifts change the size of atoms and the energy of bonds. They also move the exact color each element prefers to emit. Here is a clean mechanism that plays out quickly. Alpha sits in the Rydberg constant, which sets spectral lines. Many energies scale roughly with alpha squared. Nudge alpha by 1%, and some lines move by about 2%. Street lamp sodium glows near 589 nanometers tonight. After a 1% C drop, it would drift by 6 nanometers. Your eyes might notice a warmer hue at nights. A lab could spot this within minutes with standard gear. Spectrometers can see shifts of 1 part per million. Telescopes hold catalogs of lines across countless stars. Everyone would slide together by a matching fraction. Net result, a new C would repaint the periodic table's palette by a hair. A jet crosses the Atlantic at night under a lattice of satellites. Each satellite whispers time codes to the plane below. Position is just time multiplied by C from 4 sky beacons. Your phone does the same triangular dance on the ground. That dance breaks the moment C shifts in the void. Relativity sets how clocks tick in motion and in gravity. Both formulas keep C in the denominator squared. Change C and you change time dilation on each orbiting clock. Atomic clocks also depend on alpha, which moved a moment ago. So the reference tick itself would slide off by a percent. How would you feel that on Earth? GPS corrections already add 38 microseconds each day. Those come from relativity and altitude, not bad hardware. Receivers subtract those offsets to keep maps tight. A 1% C drop would corrupt the math everywhere. The range from a satellite is C times travel time. Get C wrong by 1% and you miss 200 kilometers. The code epoch for one satellite spans 70 milliseconds today. That distance is 21,000 kilometers in free space. 1% of that is 210 kilometers of error. Tiny tests try to drive with a map that jumps city blocks. Financial networks would desynchronize, while power grids would lose phase. Air traffic control would fall back to radar and voice fast. Emergency crews would see positions drift in seconds. So the picture is brutal for anything that needs time. Navigation that leans on C would lurch hard, then stop. Drop your gaze into the sun's core where matter is crushed. photons bounce like pinballs inside plasma that feels like steel. Those photons take eons to wander out to space, yet that wandering speed depends on C at every step. A star stands because pressure fights gravity in a fragile tie. Part of that push is radiation pressure from trapped light. That pressure scales with a constant that hides a factor of C. Lower C raises that constant and pushes outward a bit harder. Diffusion also slows because each hop takes longer in time. Energy still flows, but the tempo shifts across the whole star. This is not a flash disaster for life on Earth. The sunlight you see left the core ages ago. Changing C today retimes the conveyor, not the lamp already lit. Over thousands of years, the star would settle to a new balance. Core temperature would adjust and fusion rates would find a niche. Small changes could nudge luminosity by a few percent. Numbers help because they fix the picture. The sun's photon escape time is about 100,000 years. A 1% slowdown adds another 1,000 years to that wait. Pressure depends on 4 sigma over C times temperature to the fourth. That inverse C piece means a 1% drop lifts pressure by 1%. Stellar oscillations would drift in frequency by that same hair. Bottom line, stars would not explode, but they would retune their hearts. Now stand at the brink of a black hole where space folds. The edge you fear is the event horizon, a silent border. Cross it inward and return is impossible at any speed. That border's size hides C in a crucial way. For a non-spinning hole, the radius is 2 gm over C squared. Lower C makes that radius grow, while higher C shrinks it. A 1% drop in C enlarges the horizon by about 2%. The photon ring outside also swells, since it rides at 1.5 radii. Light paths bend harder, and the shadow grows darker at the rim. Take the monster at our galaxy's center as a scale. It weighs about 4 million suns by best current estimates. Its horizon is around 12 million kilometers across. In old C grow that by 2%, and you add 240,000 kilometers. That is roughly the Earth to Moon distance, stacked on the edge. Accretion disks would shift their inner edge outward and cool a hair. Flares would peak slightly later, since trapped light lingers longer. Tiny tests stare at the event horizon telescope image in your mind. The ring would look fatter by a few percent, not by 10. You would not see it by eye, but careful arrays might. Meanwhile, orbits of nearby stars would barely notice the change. Net result, gravity keeps control, yet horizons breathe when C moves. Pan out to the cosmic web, where clusters ride along filaments. The reach of today's universe is set by light's long march. There is a horizon that marks what can ever talk to us. That boundary depends directly on C through the universe's history. Picture the light cone as a growing bubble around every event. Increase C now, and that bubble expands faster into tomorrow. Decrease it, and the bubble creeps more slowly than before. Gravitational waves follow the same rule. Since they move at C, echoes from colliding black holes would arrive on a tweaked schedule. Numbers make it concrete. 1 light year is 1 year of travel at old C after a 1% drop. That trip takes 1.01 years. That is about 3.7 days of extra travel per light year. A star 1,000 light years away would add 10 years of delay, eventually. You would not notice tonight, yet the calendar would. The cosmic microwave background is a special old photo. Its pattern size on the sky depends on light's past run. If C had been different long ago, the pattern would shift a lot. Changing C only now leaves that pattern mostly intact. Future ripples of reionization would drift in fresh ways, though. Bottom line, horizons breathe too, stretching or shrinking with light's new pace. Now watch a cosmic ray slam into our air like a spear. It carries mind-bending energy, far beyond any human machine. Normally, nothing can outrun light in a vacuum. If C suddenly drops, that changes in a wild way. Relativity forbids crossing the limit, but nature bleeds off speed. A charged particle faster than the new C would radiate light. That radiation is vacuum Cherenkov, a strange friction from the void. Each photon carries away energy. Until the particle falls below C, the cascade would be bright in gamma rays and blue flashes. Colliders would feel this instantly in their beams. The Large Hadron Collider guides protons near old C with magnets. A 1% change would spoil synchronization around the ring. Magnets would be set wrong, and beams would crash into walls. Detectors would see showers, not clean collisions, within 1 second. Numbers give a taste. Ultra-high energy protons can reach 10 to the power of 20 electron volts. If C drops by 1%, many would sit above the new limit. They would dump energy over tens to hundreds of meters. Instruments would record sudden bursts that never fit old models. Air showers over deserts would shift shape and timing overnight. What to remember: high-energy worlds would light up with new friction. Step into a humming data hall, where cables glow behind racks. Every signal rides a path tuned to the medium around it. Space itself has an impedance that hardware quietly respects. Radio engineers call it 377 ohms as a rule. That number links to C through invisible properties of space. Change C, and that impedance shifts by a matching slice. Antennas and feeds then fall slightly out of tune. A small mismatch reflects part of each signal back to the source. Reflections stack, and bits start to flip under heavy load. Meanwhile, the physical time inside networks stretches or shrinks. Fibers push light at 2/3 of C on a good day. A 1% vacuum change still echoes inside the glass. Transoceanic paths add microseconds, and switched timing windows get messy. High-frequency systems miss their windows, and retries snowball into delay. Now add power to the picture in one more layer. The grid keeps phase with synchronized clocks across continents. Those clocks ride GPS, which stumbled when C moved. Operators would switch to local time bases within minutes. Even then, small phase errors would stress interconnects between regions. Example in plain numbers. A 1% mismatch in impedance gives a reflection of 1%. That is about 40 decibels of return loss on a line. One link can shrug that off, but thousands cannot. Bottom line, communications would degrade first, then stabilize at lower capacity. All this began with that tiny sentence: light slowed by 1%. We would feel it first in timing, then in the bonds of matter. The world would not explode, but its rhythm would slip. Instruments would groan, while stars would quietly retune over ages. If you enjoy riding through thought experiments like this, stick around. I post deep dives that stay curious and stay clear. Tap subscribe if that sounds good, and we will explore more.